If you've stuck with me for the past couple of lessons, then you've probably been asking yourself, hey, when am I ever going to design a chip select? You know, because we've been talking about really hardware level stuff. We've been talking about making a NAND gate and connecting it, well, not making a NAND gate, but connecting a NAND gate, the inputs of that NAND gate, to the higher level addresses of a processor in order to identify which device, which memory device we're communicating with. And, you know, you're probably right. You probably aren't going to be designing a chip select from scratch. Not everybody gets to be blessed with an opportunity to design hardware. You know, it's limited to just a few of us. But evidence of chip selects and the theory behind them are everywhere. So let's take a look a little bit at the theory of the chip select, because what you're really doing is you're taking a full address, and it doesn't matter whether this is an address from a processor, like a memory address, or an IPv4 address, or an address that is trying to reference virtual memory. So what we're looking at is this idea of taking a full address that has a certain number of bits. And remember that the memory space, the address space, the total number of elements we can access using this address uniquely is equal to the number of bits in that address, or 2 to the number of bits in that address. So for example, if I've got n bits that identify that address, well, 2 to the n is the size of the memory space that is referenced by that full address. Now, what the chip select says is that I can divide this address into 2 pieces. This portion right here identifies the device, right? And whenever it came to our memory devices, those were the bits that we put into the chip select, into the NAND gate in order to activate the device. These bits right here go to the device, so they're address bits to the device. Now, the number of bits, let's just say that there are m bits, well, then the size of the device that we're accessing, it's 2 to the m, right? 2 to the m unique addresses, all right? So, whenever it comes to, I can actually, there's all sorts of things or ways that I can apply this theory. For example, let's say that I have a processor that has a, I don't know, how about, let's just say a 256 meg memory space. And it's trying to communicate to a device, so we have this memory device. And once again, this memory device could be hardware. It could be a graphics card. It could be a network interface card. In fact, in the case of whenever you start doing things like embedded system designs, where you're designing processor systems that are communicating with hardware, directly with hardware, things like serial communication ports, or just simple I/O, you know, or do I want to turn on an LED or read the value from a switch? They're going to be what we're called memory mapped to the processor. And so they get addresses just like a regular memory would. But let's say that we're trying to talk to and trying to communicate with a 32 meg memory, all right? And let's just say that a random address within the memory, let's just come up with something. How about, I don't know, so 256 meg. And by the way, 256 meg, that's equal to 256, which is 2 to the 8th, right? Times a meg, which is 2 to the 20th, which means it's 2 to the 28th. 256 meg is 2 to the 28th, which means our n is 28. So we know how many bits the processor has. 28, that's 7 hexadecimal nibbles. So let's just say we're trying to communicate with a hexadecimal value. I don't know, how about 9AB2CD5? So let's just say that that's an address within the memory. Now, this is not quite the way the design works out, but I'm just trying to give you an idea that if we know these 3 pieces, how many, and that's all you need to know is those three pieces. How many bits in the full address, how many bits go to the memory device, and what the pattern of ones and zeros are what the patterns of ones and zeros is that defines that device. And we've got all three of those things here with this information. So 32 meg, well 32 is 2 to the 5th, right? And a meg, once again, is 2 to the 20th, which means we have 25 address lines coming from or going to the memory device. And so if we break this down into our pieces, right, what we've got is the number of bits here, and it is what, 25 bits? And then the number of bits here is the remaining ones, so there's 3 bits left over. Now, what's the pattern of ones and zeros for those 3 bits? Well, all we really need to do is see what the most significant 3 bits of that hexadecimal number are. Well, if I've got 4, 8, 12, 16, 20, 24, 28, there's all 28 bits. So this most significant nibble, 9100, that's what that starts off with. And so the most significant address line, so there's 28 bits, that means A27, A26, A25, those are the 3 most significant bits whenever it comes to communicating with this device. Just put that into a NAND gate. A27 needs to be a 1, A26 needs to be a 0, A25 needs to be a 0. All right, so those are the 3 pieces. Now, this actually applies to a lot of things other than, as I mentioned before, than just simply memory addresses. Let's say, for instance, I've got an IPv4 network, and if you're not familiar with networking, what you've got is this address that takes 3 pieces. You've probably heard something like this. So we've got an IPv4 address. We'll call it 192.168.1.42. All right. So there's the address. Now, what this really is 4 decimal representations of 4 individual bytes. So there's 8 bits for 192, there's 8 bits for 168, there's 8 bits to represent 1, and there's 8 bits to represent 42. So if we convert this to binary, we get 192 in binary is 11000000, and then 168 is 10101000. And then 1 is basically 7 zeros followed by a 1. And then 42 is 000, no, not quite. 00101010. All right? And so that's the address. And so whenever you look at representing an IPv4, we use IPv6 for larger scale stuff, but for local stuff, we're still using IPv4. And so we've got this IPv4 address. How many bits are there? How many bits are there? Proper English there. So we've got 8, 16, 24, 32 bits. So in the case of IPv4, our full address is 32 bits. What is our memory space then? In other words, how large a network can we have? Well, that's 2 to the 32, which is equal to 2 to the 2 times 2 to the 30th, which is equal to 4 gig. 4 gig. 4 billion addresses. That's a lot, right? Turns out it wasn't enough, but yeah, it's a lot. It's a lot. You know, now that every light bulb on the planet has its own IP address, we probably didn't make the network big enough. Now, you're saying, okay, well, what does this have to do with this chip select thing? Well, it turns out that every single IP network has something called a subnet address. All right. This is an address that refers to just that little portion, just like with the memory, you know, we're looking at we're just accessing a single device within the full memory address space. A subnet address says within the network address space, these addresses logically identify just a small portion. Now, Usually, well, always, what is configured on a subnet is something called a subnet mask. Now, a subnet mask is usually, it takes the form of something like 255.255. And we'll just go 252.0. All right. Usually starts out with a couple of 255s. Now, if you're familiar with binary conversion, you know that 255 is all ones in binary. So if I put this subnet mask below this address, I'll have 11111111.11111111 dot. Now, 252 is 3 less than 255, so these least two significant bits, the 2 and the 1, they turn to 0. So we've got 11111100 dot. And then 0 is just all zeros. Notice anything? Notice how the pattern of ones and zeros in the subnet mask kind of matches this idea where something is different on the upper half of the address or the upper portion of the address than is on the lower portion of the address. Yeah, what you've got is your line, the line that divides the device identifier or the subnet identifier from the individual addresses within the network. Now, if I were to go ahead and, if you remember your bitwise operations, perform a bitwise AND. A bitwise AND would give me 1 and 1 is 1, 1 and 1 is 1. So this right here, this right here is bitwise AND of the address with the subnet mask. So, whoops. We'll do a 0, 0, 0, 0, 0, dot 101010000 dot 000000000000000. And so whenever you do a bitwise AND of the IPv4 address with the subnet mask, the one that corresponds to this network, what you do is you strip out all of the lower bits. You strip out all of the address bits that refer to an address within the subnet. And you just get this pattern of ones and zeros, which identifies the subnet. So for our particular address and subnet, what you've got is, this is let's write this normally. So this is, or in decimal, that's 192.168.0.0. So there is the subnet address. So if you wanted to refer to just the subnet, that's the address you'd get. Now, if you inverted the subnet mask so that there were all zeros up to this point and then ones for this portion, what you would get after doing a bitwise AND is something we call the host ID. And so the host ID itself is just all zeros. In fact, let's go ahead and make another entry for this. The host ID is, so it would zero out all of these bits and copy down the host ID bits, giving us 00142. Now, that address in itself is useless. But what happens is that once your message gets across the network to this particular subnet, it's able to say, okay, found the right subnet, now which device within the subnet is there? Kind of like memory. Once I find the memory device, which address is it within the memory that I'm looking for? All right. Now, as I said before, evidence of these chip selects or this type of theory is all throughout our computer. For example, take a look at this device manager screen for a typical computer. If you look at the device manager, there are a number of hardware devices that are connected to this machine. Let's go all the way down here to the bottom of the USB controller and take a look at the actual host controller itself. Right-clicking on the host controller opens up this little context-specific menu, and I can select properties. By going to resources, I see something called a memory range here. And that memory range looks oddly familiar, doesn't it? In fact, over here, let's just go ahead and copy down these values. So I have A 1, 7, and then 5 zeros, right? So that's the low address. And then I also have A170 and then 4 Fs. That's the high address. Let's convert this to binary. And so we've got 1010, 0001, 0111, and then 20 bits worth of zeros for those 5 nibbles of zeros. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, now let's take a look at the high address and convert the high address. A is 1010, 1 is 0001, 7 is 0111, and then we have a nibble of zeros, and then we have a bunch of ones representing those 4 nibbles. We have 16 ones representing those 4 nibbles of Fs. All right, now, if you look here, that's the section that identifies the device. How many bits are there? Well, 16. So the memory range, the space in the processor's memory map that this takes up is 2 to the 16th, and 2 to the 16th is equal to 2 to the 6th times 2 to the 10th, or 64K. So we have a memory range. This USB host controller has a memory range of 64K. All right. Now, the bits above that is what defines the chip select, or what activates this particular device. Now, it's done in the electronics. It's not necessarily done with any sort of a NAND gate, but it is the same theory. Now, I don't know how many leading zeros to include, so I don't know exactly what the memory range of this processor is, but there are some leading zeros there in order to increase the available memory that's on this machine. All right, so let's cancel this and let's go up to, how about display drivers? We'll right-click on that, go to Properties, and go to Resources, and we see that this device actually takes 2 sections of memory. One starting at A, followed by 7 zeros, which when you convert to binary is 1010, and then followed by 7 nibbles worth of zeros. And then you have a high address of A0, followed by 6 Fs. So when we convert that to binary, it's 1010, 0000, followed by all of those Fs. And once again, we see that there is that line drawn between where the bits are identifying the device. That's the 10100000. Those bits are identifying the device, and then everything to the right of that, those are the address lines identifying the unique memory locations in that memory range for this graphics card. How big is that memory range? Well, there are 6 nibbles worth of Fs. Well, 6 nibbles worth of bits that go from all zeros to all ones. So that gives us 2 to the, 6 nibbles is 24 bits, so 2 to the 24th, and that's 16 meg. And that's just one of the memory ranges. The other memory range goes from 9 followed by, 7 zeros, and that would be in binary 1001 followed by 7 nibbles of zeros, that's 28 bits of zeros. So then up to our high address, which is 9FFFFFF, which is 1001, and then 28 bits worth of ones. And we see once again, we've got this line that divides the bits that stay the same, the 1001, that identifies the device, followed by the 28 bits of all zeros going to all ones. That is the address within that memory range. And so we've got 28, what's that? 256 megs. So this particular graphics card has one section of memory which has 24-bit address, or 16 meg. The second section of memory that it uses is 28 bits or 256 meg. So that shows that those ranges are what are used in that particular graphics card. Let's take a look at one more just in case you didn't believe me. How about looking at a network adapter? So we come up here, we look at its resources. Also, 2 sections of memory that are being used. Now, both of these sections of memory look like they're about the same size, but they're in 2 different portions of memory. One starts at A15, 00000, and the other one goes up to A15FFFFF. All right. So that converts to 1010, 0001, 0101, followed by 20 zeros. And then the next one, the high end, 1010, 0001, 0101, followed by 20 Fs. Now, this section right here, that is the unique identifier, and notice it doesn't match any of the other memory ranges that we look at. These memory ranges cannot overlap unless they are on a separate bus. And then these right here represent the size of that memory space. And since there are what? We decided there were 20 bits in that section, so it is exactly 1 meg worth of addresses. Now, that gives you a little bit of an idea of what we're talking about whenever it comes to the resources on your machine. But it's not limited to just the resources on a desktop. You can also find it on devices such as the Raspberry Pi. So let's take a look at its memory map. Now, I don't mean to scare you with this particular image, but I did a real quick search on the web for Raspberry Pi memory map. And, you know, it is a little complex, but please ignore the memory maps that are to the left of this. Let's just focus on just the memory map that's to the right. This shows us basically the exact same information that we've been looking at other memory maps. It shows us how big the memory space is for the Raspberry Pi. It goes from all zeros up to 8 Fs, and so those 8 Fs represent a 32-bit memory space. 32 bits, that's 2 to the 2 times 2 to the 30th, which is equal to 4 gig. So it has a 4 gig memory space. But really what I'm looking at here is the very top section of this memory map, the one that's labeled I/O peripherals. I/O peripherals, well, that is the set of registers, and there's a number of them, that allow us to configure all of the I/O devices that are on this chip. So if you want to be configuring any of those directly using memory locations, you've got a base address of F2000000 that is where all of those registers start. You can only find this by looking at the memory map. Now, if there's a particular register that you want to configure, there's an offset from that base address. So let's say I want to modify whether a pin is an input or an output. There is a configuration register that will have an offset. You add that offset to F2000000, and you get the address of that register. It gives you a lot of control over the I/O devices in the Raspberry Pi. Now, the thing that's really important is that Raspberry Pis, as they've gone through different generations, that base address has changed. You can only get that for the memory map for that particular version of the Raspberry Pi. I think this is for the Raspberry Pi 4, but I'm not sure. The offset for each one of the I/O peripherals doesn't change, but that base address might. So anytime you're doing any sort of interaction with that memory device, just use the base address added to the offset. If you changed from a Raspberry Pi 4 to the 5, well, if that base address changes, all you have to do is change that base address in your code, and your code will still work. Sorry about that. That could have been a little overwhelming to some of you. But the idea is that if you understand how chip selects work, how you can access different resources inside of the processor based on their memory address, wow, you've got a lot more control over your processor and can actually get a lot more in depth or get a lot more control over your designs.